2 more weeks of a different topic, which is, however, very important and one of the strong features of my field. A lot of research has been done since, I don't know, 40, 50 years or something. It's really insane the amount of work you can the amount of work you can save with this kind of technology. So we have another 2 weeks block this week and next week. I'm motivated again with a couple of applications. Actually, it's many applications that benefit from the technology you will be learning today and next week. So, and then second will be, of course, to look at the data management and analysis issues behind that. So this is more the data management part. So there's, you sometimes see these terms with regards to data, that people analyze data and people manage data. So this is more about data management in the sense changing data, inserting, updating, deleting data, not so much the analytical part. So we are focusing more on changing data and what may happen if you want to do that. Yeah, then we look at a couple of basics, a bit more slides, a bit more theoretical this time, and then finally we transfer that to the concrete application, what that means. So I coined this 2-week block trading, banking and ticket system, and that was motivated by real events here. So it's always in German and in English, the translation in English. A couple of years ago when that happened, we had in Germany a lot of interesting breakdowns of IT from very big German banks. And the Deutsche Bank, German bank is a very big German bank, and they had really terrible IT problems, and that happened to many other banks as well, in Austria as well, or UBS, that's the Swiss bank. The effects on customers was pretty severe. So in some cases, the rent for the apartments wasn't transferred, which really has legal consequences if you don't pay to your landlord, because they may fire you. People didn't have access to their money. The cards didn't work, the ATMs didn't work, stuff like that. It was completely crazy. And the bad thing was not that these things happened. It's okay, the computer systems break down, but the really terrible things, the really bad thing about that was that it took so long to recover the systems. It was days or weeks in some scenarios until the systems were fully up and running again. And that's really not understandable from the point of view of today's computer science. So I want to go a little bit into which techniques you should use and to avoid these kind of situations, and why this is completely non-understandable to me, why these things happened like that. So there were many reasons for these failures and these scenarios. Very different. I heard from some insider what happened at that point in time was really a super stupid software engineering thing they did, which broke down their production system. But as a computer scientist, you can ask yourself, why do these outages take so long? Why does it take so long to recover the stuff? Why does it sometimes take so long to get the systems back and running to a consistent state and resume normal operations? Why are there so many failures? Why are so many customers affected? It's also a very important thing always to consider when building systems. Yeah, it's nice if you have these toy examples and you play with that in a lecture, or you have 20 users on your website, but we're talking about systems with millions of users. Yeah, and you always have to multiply the time, or the loss in lifetime, so to say. Yeah, if every of your customer loses 5 minutes times number of customers, that's a lot of time you're wasting. So so in particular for very big systems with many users, you have to be super careful, because every small bug can have consequences for so many people. And in particular for banks, I mean, it's really surprising that given the money they have at their hands and the investments they took, why don't these systems run more stably? So there are, when dealing with data, there are numerous possible and typical sources of error, sure, but they have been known for decades. And if I switch into a little bit of an arrogant mode here, I would say, yeah, and there are solutions as well. So I think all of these things could have been avoided in the first place with very simple, this is an undergrad lecture stuff. Yeah? Undergrad lecture would have prevented these things in the first place. Why? Because these things are all available and can be avoided easily if you use what we call a database management system. So I've touched the term here and there in the lecture already, and I want to define it a bit more properly. So a database management system, or DBMS for short, is a technology that has been developed since the 70s. And it's a big toolbox, it's a big black box, if you wish, of fantastic technology that helps you solve many, many data problems. So modern database management systems have the following features typically. So relational model, we learned about that, but they have an extended version typically. Let's make it a little bit, something like that. So have an extended relational model where you not only store attributes, integer values, and strings, but you can store all kinds of stuff, JSON, arrays, text, spatial data, and so forth. Yeah, very extensive SQL dialect. It's really insane, the SQL standard, how big it has become. I think it's like 2 meters on a bookshelf or something like that. We really touched super simple SQL statements now, only the very basic stuff. There's so much more contained in SQL. Automatic query optimizer, we learned about that. So join enumeration, whether to use an index or not, rule-based optimization, cost-based optimization, we learned about that. That's basically what most of the database systems have today. Then very high performance. That depends a lot on the query optimizer, of course, how good that is. But typically database systems are super fast these days. Massive support for physical design. So by physical design, mean that you can give hints to the database system which indexes to create, which data structures to create, how to partition the data, how to cache the data, what to materialize, and so forth. Support for modern hardware is another strong feature of database systems. So until, I don't know, 20, 30 years ago, most database systems operated on hard disks, the thing with spinning platters. Now it's mostly in main memory. Most of the world's database systems sit in main memory, and you get a lot of performance due to that, but you can also build the database systems differently. Now there's persistent RAM, FPGAs, GPUs, TPUs, all kinds of stuff, and many people are working on adapting database systems to new kinds of hardware. But when it comes to avoiding and dealing error situations, there's also a huge set of algorithms that's shipped with database systems. So there's extensive support for transactions and ACID. That's what we will be learning about today as well, what that means in detail. There's concurrency control, and by that I mean automatic concurrency control. And what that really boils down to is, so what was very early seen for application developers, that application developers have a hard time doing multi-threading themselves, locking some data item and making sure that the system doesn't starve and is alive, and all these things you might be learning in a concurrent programming lecture. So the idea of databases was early on, this is too complex and too error prone. We can't expect our users to do these kind of things because it's too complex. So why not build it into the system and handle it automatically, such that users don't have to fiddle with threads anymore. And that is super cool, because now you have a set of experts solving the multi-threading stuff, and the application developers, the users of the database management system, don't have to worry about this stuff anymore. And this is important to understand, because as a computer scientist, you might be tempted in a situation where you feel like, oh yeah, I have so many cores and so many CPUs, let's do some multi-threading. The first question you should ask yourself, can you use the database system and delegate it to the database system? That's again a laziness principle in action. First thing to ask is that something that's suitable to be delegated to a database system because it can solve it for you? Rather than you implementing it and introducing bugs and having to, I mean, if you ever tested multi-threaded programs, it's a nightmare, right? Or what may happen. So the first reflex should always be, is there a way to use the database system to handle the concurrency, the multi-threaded problem here? And that makes it so cool. So I'm not saying that you should never ever program with threads anymore. There are use cases for that, for instance, in high performance computing, or when building a system and implementing the internals of the system. That system could be a database system, for instance, graphics, high performance situations, neural networks, whatnot. There are situations, but I would claim 95% of the cases, even more, can be delegated to a database system. And that's what we will be looking at today, how that works, and next week as well. It's a big topic. Yeah, then there are more topics that we don't handle here, but are also part of a database system, and that is automatic crash recovery, replication and backup. So those are things, if you go back to these scenarios, yeah, so the system crashes, in whatever state. Maybe some data was in main memory, you have a power failure, data gets lost, some other data was stored on the disk, yeah, and still there. You fire up your database system again, and you may expect it to be in an arbitrary state. Everything that is in main memory was lost, everything that was on SSD is still there, so you have a mix of data that's still there and that's not there. That's what we call an inconsistent state. But the good news is, since the 90s, database systems have incorporated algorithms that handle that. So if you configure your database system well, doesn't matter whether there's a power failure. You switch it on, the database system will fix everything for you. And then it says, hey, here you go, here's your data, go ahead. And that's a couple of seconds or minutes, and then the system is up and running again. So what I'm saying is, if you screw up your data, it's probably the user who misconfigured the database system. Yeah, consistency control is another thing that you can do, dynamic views, access rights, and so forth and so forth. But today, and that goes back to the teaser slide. I used to advertise this lecture and this kickoff meeting. So all these weird acronyms I use here in the abbreviation. We will get to those acronyms pretty quickly in a moment. But there's all this automation, all this idea of, this is complex, this shouldn't be left to the user. Query optimization, index selection, concurrency control, all these things, we automate all of that and then make life simpler for the user. That's the idea of a database management system. Okay, the analogy I will be using is this car that's called the A-Klasse, German, built by Mercedes in the 90s or something like that. Has any of you seen that car? Yeah. And it became very famous. Mercedes wasn't happy about that. It became famous because there's a test they do with cars. It's called the elk test. And the idea is the car runs down the street, typically in Scandinavia. That's where they do final testing of many of the cars. And then there's the elk, an elk, this big animal, entering the street. And then the car is supposed to brake and make a turn around the elk to not hit the animal. Yeah, and the car failed. The car toppled to the side, did a somersault, and didn't stay on the wheels. And that was pretty bad. It had to do with the car being rather short, and the center of weight being rather high. That was a huge problem. And they detected it very late in their testing pipeline. The car was already designed, everything was ready to be built, and then in the very final stage they found out, oh shit, we have a problem, this car is going to topple, and that's really endangering the users. So, oh my gosh, what are we going to do? Yeah. And it had to do with something like that. So that's basically what you, at least in Germany, that's a common thing. You have these three pedals, acceleration, clutch, and brake that you use. And it turned out, actually, it would be so much better, and you could avoid all of these dangerous situations if you extended your brake to be like that. Yeah, imagine you had one brake pedal per wheel. Yeah, it would be, you could avoid the car being falling over and toppling and stuff like that. Just adding more brake pedals would fix the problem. I mean, this is awesome. Why not change the user interface for the car? But it's a great idea, yeah? But it turns out, maybe imagine you had to now operate with your feet like four, and then you have to listen, how do I do bottom left and back right, and with your foot, it's kind of it's not that easy, right? So, so basically, what happened was, so before 1997, that's when that happened, you had this, oops, I said zoom in. You had something like that, and then that would be probably the change to the user interface, plus the incredibly talented driver that doesn't exist, I guess, to handle these kind of situations. In particular, when you're in shock and something happens, then to do something with such a user interface, well, maybe not. Yeah. But the solution they came up with is something like that. And that was, okay, we keep the user interface. We assume the users are overwhelmed and they won't be able to handle 4 brake pedals. But we do some automatic braking of the individual wheels. And that was called ESP, Electronic Stability Program, or something like that. And one of the core ideas was there was a computer sitting in the car watching what the car was doing, and then the computer could individually brake individual wheels, or release the brakes and stuff like that. And with that, the car was able to not topple, to avoid the toppling. It was really cool. So, and actually, it became very popular. Other car manufacturers picked it up, and it became even mandatory since 2014 because the numbers were clear. You could avoid so many accidents with that. Yeah? It was really a cool invention, invented because of a problem of one car manufacturer. Yeah? And that's the same thing. Yeah? So what I'm trying to tell you, that is multi-threading in the middle, of course. And we don't do that. We say, okay, give the user an interface that doesn't look like multi-threading, looks like single threading, but in the back there's some computer machinery, the ESP. The ESP in the database is called concurrency control, handles all the magic, all the difficult stuff for you. And that's the cool stuff about this approach. Okay, so there are many different database management systems out there, and because it's so important, and basically every software you build, or almost all software you build, at some point you bump into, hey, we need a database system. So it's $1 billion market. And there are very famous companies like Oracle. SQL Server is a system built by Microsoft. HANA is a product built by SAP. Access-Hall is a very fast analytical database system built in Germany, actually. A couple of open source systems. We bumped into SQLite and DuckDB so far, but there's also MySQL and Postgres. Postgres is super popular for real production systems. Yeah, if you build a web application, you probably want to use Postgres. Yeah, that's fantastic. Has everything you ever need, or covers the 99% case, I would claim. And there's a database of databases, actually. So that's a website where you can look at the different databases that are known. So as of this morning, it was more than 1,000 different database management systems. Yeah, not the data in databases, that's not what I'm talking about, really the software, 1,038 different software products that are database management systems. Always different features, of course, but yeah, so a lot of things going on there. Yeah, so important to understand is so far what we did here was we had Jupyter notebooks, and we load CSV files once into relations, Python, SQLite, DuckDB, you name it, all in a single thread. Then any number of, this microphone is a bit loud, isn't it? Then any number of read queries are issued on the relations, and reread stuff. Yeah? So we basically just took our database and read information from that. That's what a select star, whatever query is doing. You read information out to the client using the database. So there's no problem with concurrency by definition. If everyone is reading, there's no problem. Nothing can go wrong. But now we change that. Now we allow queries to change tuples in relations concurrently in any way they want. Yeah, so they might be multiple threads operating on the same database, and you somehow have to synchronize here. You somehow have to do something about that to not screw your database. So the problem scenario we look at first is something like that. Yeah, there's a bank, that's a classical example, and yeah, you can represent accounts with a single relation, accounts with 2 columns, number, that would be your account number typically, this long IBAN number, and that's what you have on your account. That's all you ever need to represent to run a bank, actually. Okay, plus legal requirements and names of customers and stuff. But for this use case, that's enough. Number is a primary key, and that's all you need. And then you have bindable customers accessing their accounts. And now we can look at different scenarios that may happen, different interactions with that accounts table. But in general, you have multiple customers. Want to access their accounts at the same time. At least one of the customers changes. Again, if everyone is reading, there's no problem whatsoever. But maybe at least one of the customers is changing the account balance by withdrawing, depositing, or transferring money to another account. That's the scenario I will be talking about. So let's assume at any time a maximum of one customer accesses the accounts relation. That's what's happening here. So I use it with a traffic light symbol. See, everyone is blocked from the bank and only one customer is allowed to access the bank. So the best analogy for that I'm seeing is really, assume you go to Mensa. And there might be concurrency issues, people trying to grab the same tablet, the same plate at the same time, trying to sit on the same seat at the same table at the same time. That's a concurrency control problem, multi-threading, each student being a thread. So, I mean, it would be a great idea to avoid these situations to just allow one student at a time to eat at Mensa. That would fix the problem. You wouldn't have any problems anymore. Students couldn't go into their way. So you have one student entering, fetching the food, eating the food, and after 45 minutes, the second student could enter. Then the third, the fourth, the fifth, and the sixth. That's what's on this slide. It's not so efficient, but it's correct. Don't have to worry about that anymore. And you may be tempted to think that this approach is absolutely stupid, but there are actually situations where it makes a lot of sense, because when you think about how fast computers have become these days, it could be that the stuff one student is doing can be super fast. If you think about if what this account owner is trying to do is change the account balance. Maybe let's assume this person wants to add $100 to the account. How long does that take in a modern computer? What do you think? What is the right unit? Maybe there's network stuff, right? Sure, right, some server. Let's ignore network for the moment. Just on the server, and assume we are already on the server. How long does it take to change an entry like that? What is the unit? Is it seconds? Is it minutes? Is it, 10 server ticks, that's a good unit, So clock rate, and depending on the frequency of the CPU, you can count the number of ticks in the machine. Other guesses? Depends on many things. The one thing is CPU. Of course, there's memory involved, so it hinges on the memory of the speed of your memory. How long does it take to write stuff to that memory? But if it's DRAM, the unit is nanoseconds. If that is backed by a hash table, what makes a lot of sense, a hash mapping keys, the numbers, the bank accounts to values, which is a balance, then you can expect a couple of 10 million, a couple of dozen operations every second. And that is a single thread. So totally crazy performance you get from a modern machine. And then there's always a balance. Oh, should I really implement concurrency control? Or maybe I can fix it by queuing all of the requests in the first place and then replay the queue on my hash table. That's another approach, and that's not so stupid. So this analogy with the students' canteen, with the Mensa, in real life doesn't make any sense. It's completely stupid because the individual time a student takes to eat is too long, but in a machine, very different story. It could actually be an interesting solution. But anyway, let's assume we really want to fix it algorithmically. And what could be a better approach? So assume at any time a maximum of one customer accesses a tuple of the relation accounts. So what you limit here is you say, okay, that's fine. Typically, these customers, if they withdraw money or put money on their bank account, it's their tuple anyway, if they don't share an account. So you could limit and say, okay, every tuple is at most accessed by one customer at all times. Then there's no conflict. Nothing can happen. Everything is fine. It's the equivalent of saying maybe in the Mensa, what would be the equivalent? Maybe on each chair in Mensa, at all times, only one student can sit. They cannot sit on top of each other. That could be the equivalent, and already brings you pretty far. So you could block the access to the respective tuple and come up with a mechanism that makes sure that this constraint is fulfilled. Everyone asking for a chair first has to check whether the chair is free. And only if that chair is free, the student can sit on the chair. Same with tuples. First check whether the tuple is currently not used by anyone else. Only if that is the case, you can do something with that tuple. No? But conceptually corresponds somehow to a queue per account or per tuple. So it's not a queue per bank or queue per Mensa, it's a queue per account or / seat in the Mensa. So conceptually, the client owns his or her account for a short time. It gets a bit more complex if you now start transferring money. Yeah? So now assume a situation where you want to transfer money from one account, let's say account 2 to account 7. So now it's more than one tuple now. Yeah? So it's not the same situation as here, where it's just about adding and removing money. Now that's two tuples. Yeah? And if one client one customer issues a bank transfer, okay. Yeah, so we have to think about that. So maybe we could do something along the lines of you block the access to all affected tuples, which is usually 2 within a single money transfer. Maybe you could do something like that. Huh? But what happens if we have then multiple of those transfers, so situation like that? So there's a transfer going on from account number 2 to 7, and somehow at the same time another transfer for 200 euros from account 7 to number 4. How does that interact? What happens? Can that go wrong? Stuff like that. Yeah, so you have to be careful, because this leads to a problem that's called serialization, also sometimes called linearization. Slight differences, but we will call it serialization in this lecture, where you have to decide which operation, which money transfer is executed first. We will talk about that in a lot of detail in this lecture. And there could even be situations that you try to simultaneously transfer 100 euros from this account to that, and at the same time 200 euros from this to that. And that could actually bring down the system, that could jam the system, which is called a deadlock in concurrency control speech. You could really, the system could be so locked that there's no further processing possible. And you have to be able to detect that and fix it. Otherwise, every time that happens, you bring down the system. You don't want to do that. So, 2 questions here. How do we allow concurrent modification of data without creating erroneous data? Automatically, how do we design this so that the process and the resulting overall system are efficient? You can always come up with something slow, but we also want to be efficient. We want to allow users to make use of the threads. Yeah? If he creates automatic concurrency control that cannot leverage the computing power of the machine, well, that's not so great, maybe. Huh? Okay, so there is a lot on our agenda, and so I introduced that. We will start with some very basic terms, and then we enter serializability theory, some terminology I have to explain, and then I explain one class of algorithms based on locking. There's another class of algorithms called MBCC I'm explaining in the core lecture only, but you first have to understand locking-based protocols, also some abbreviated as 2PL, before it makes sense to explain MBCC to my understanding. Yet you will see that most database systems today use MBCC because it has a couple of interesting advantages. If you're interested, there's also, I have videos on that on my YouTube channel where I explain MBCC in detail. So if you don't want to wait for the core lecture, you can also do that. Okay, so let's first look at read operation versus write operation. So read operation reads at most one tuple from one relation. That's what I'm simply going to define in this lecture. You can change that, but for the moment, to simplify matters, that's what I will be assuming. So the tuple is the granule we will be operating on. Not an attribute value of a tuple, but really a tuple. That's our smallest unit, so to say. And the notation for that is the small r, and then, so this is the r, and then the a. A is the data object I'm reading. So typically, the attribute values of a tuple, or at most, the entire tuple. That's the notation we will be using in this lecture. In contrast, there's a write operation. It can be an update, an insert, or delete operation. But for the moment, think along the lines of updates. Most of the scenarios, most of the things I will be explaining will be along the lines of updates. But later on, we will look into inserts as well. Any change operation, you change somehow the database by changing a tuple, adding a tuple, removing a tuple. And again, this is at most one tuple for the moment. One tuple is changed, not multiple. And the notation for that is WA, write data object A. So the attribute values of a tuple are somehow changed. At most, the entire tuple is updated somehow. And what is the relationship to SQL? Well, in SQL, this read operation typically corresponds to something like this. You have a lookup in a relation using the key of the relation, here the ID column. And if you have a where clause like that, that makes sure that you get at most one tuple from such query, of course. If the tuple with ID 42 exists, you get a tuple. If it doesn't exist, you don't get anything. And then you select the attributes you're interested in the projection. So what the read A actually means here is just a shortcut. Actually, I'm reasoning about SQL statements, how they interact, different users sending SQL statements to the database system, but it would be too awkward and to write every time a SQL statement. So that's why I'm introducing this abbreviation, because it is enough to illustrate the problems. And the same abbreviation for writing, the write, and then the data object A is being written, is basically something like that. Yeah? You do an update, again, on such a condition, restricting it to one tuple, setting the new values of the tuple, and then here that's the relation name that you're updating. Yeah? And that could be an insert, again, it could be a delete. Yeah? All of that is abbreviated with you write A. Okay. Yeah, so that's what I said. All of these happens via the key of the relation. That's very important. In all of these SQL statements, I assume that these where clauses select at most one tuple. Okay, that brings us to the term transaction. That's maybe one of the most fundamental terms in my field. What is a transaction? A transaction T bundles one or more read and write operations into an inseparable unit. The transaction defines the conceptual order in which its read and write operations are to be performed. The notation here is that we notate the beginning of a transaction with a B for begin and the successful end with a C for commit. And then we have this notation X precedes Y, saying operation X takes place before operation Y. Each operation must take place after the begin and before the commit or abort. For instance, if you have a transaction 1, the money transfer we just talked about from account 2 to account 7, as of above, we could denote it as follows. So we have a transaction that's beginning, the ID, we number these transactions, they all have unique keys. Transaction 1 begins at that point. Then it reads K2. Now here I'm assuming that that is the account number 2. Then it writes account number 2. And then it reads account number 7. And then it writes account number 7. And then it commits, meaning the changes done here are now persisted in the database system. That's the stuff we will be looking at. That's called a schedule or history for a transaction. And the important thing to understand is, if you look at that, I mean, at no point in this write-up did I say how much money is being transferred. Yeah? So when you use a database system, it's always like you have your programming language code and then you send SQL statements in between, or in Django, it's the same thing. You have Python and then you have these, okay, that's safe, yeah? You modify the object and call save. But what the database system sees is a list of individual statements. So in a money transfer, the database system sees one SQL statement, select, tralala, konto from the stuff we saw here. Yeah, so the first would be something like that. That would be the first statement the database system sees. Yeah? And then the next would be an update statement on the same tuple. Then another select, tralala, on this tuple K7. And then an update operation on the tuple K7. So this is just a shorthand, again, for 4 different SQL statements. Yeah? And that's all the database sees. The application code issuing these commands is not sent to the database system. So the database system only sees the SQL stuff being sent. Yeah? So we have to live with that. Yeah? All we see is SQL, and based on the SQL statements we see, we have to make a decision whether these things are allowed or whether they're not allowed, or whether there can be any problems. And that's very important to understand. So in databases, you always have these terms host programming language and SQL. So SQL is somehow embedded into Python. It's embedded into C++, Rust, and whatnot. Huh? It's kind of 2 different languages that are forced into marriage. That doesn't really work, actually. So there's a lot of discussion going on how to change that and make it better, actually. We're also working on that in my group. But that's how the world is. Yeah? You have a programming language, and you send SQL to the underlying database system. Yeah, that's what I just said. So we only see read and write operations. So we are in the database system. We see the SQL commands. We don't see the application code. And we have to live with that to make a decision whether there's a concurrency problem or not. So I think we can safely skip that. That's a more formal way of defining a transaction. But yeah, I think we can read that back home. We don't need that here. That we need. So the state of the instance and sequential versus concurrent execution. So if you have a transaction, Ti, that is executed on a relation R and commits, and you can do the same notation if you have multiple relations. So I'm restricting it to one relation here, but you can also do it for multiple relations. Then we denote the state of the instance of the relation after executing the transaction as that. So that's the state of relation R after Ti was executed. So whatever changes were present in Ti, they were now applied to that relation R. R reflects those changes. Yeah? That's the idea. With that you can do a sequential execution or concurrent execution. So that's the notation here. That is this one pipe symbol here, yeah, saying, okay, I first execute T1 and apply it to R, and once all of that was applied, I execute T2. Again, that's student 1 entering into Mensa, being alone, doing all the changes, like removing food from the state of the student's canteen. And once student 1 is finished, student 2 enters, removes some more food from the kitchen, eats it, and leaves Mensa. Serial execution, one after the other. Versus concurrent execution, we have these 2 pipe symbols saying, yeah, anything may happen. 2 students are the students in Mensa at the same time, and they interact in whatever ways, no idea whether that broke something in Mensa. Yeah? That's the 2 kinds of notations we're using. Yeah, and that brings us to what's called ACID, the ACID properties. Well, that was done in the 70s, and there were a lot of drugs people were using, and then a lot of the technology in databases is still influenced by the names of the drugs back then, actually. Yeah? I don't know. There's also, in software engineering, there's actually LSD. It was used multiple times to name stuff. Yeah? I'm not sure how it is in 2025, whether computer scientists still name their techniques after drugs. I don't do that. I don't take drugs. I don't name my methods like that, but just as a little bit of an excuse. Acid was a drug in the 70s, and they used it as, which has now become one of the most fundamental principles in database systems. Okay, I'm not sure whether that was intended, probably not. And each of these letters stands for one concept or one property transactions must fulfill. Yeah, so now we talked about transactions, and now I want to decide whether the transaction is good or whether it's bad, whether it fulfills a certain set of constraints or not, and that's called ACID. So let's look at the different letters. The first is atomicity, A. That means a transaction is an inseparable unit. The read and write operations of a transaction are either executed completely or not at all. This is also called all or nothing. Yeah, whatever the transaction does, you execute either all of it or none of it, but not like half of it or the first half and the second half. That's with our example, assume a fully executed transaction would be something like that. Yeah? All of the read and write operations were executed. But if it was executed partially, it could look something like that. So here you see that the write operation is missing here. There's no write operation here. That happened. What does that mean for the bank? This line where I just wrote, what does it mean for the bank and for the customer? Yeah? You might withdraw? You might be able to withdraw the same amount once again. Yeah, okay. But if you assume that the write 1 to K2 happened in the database. Right, if you assume that you remove here, you remove some money there, yeah, then you write it in the W1 K7 to the target, it never arrived. What does it mean from the point of view of the bank? Huh? Yeah, the bank, the amount was removed from one of the customers, but if it's backed by real money, the bank wins. Yeah, so if in doubt, the bank always wins in these scenarios. Yeah?
It's exactly as burning a bill.
Huh?
It's the same as burning a bill.
Burning a bill? Okay, that's the same. You burn your bills, but yeah, but they will send you a reminder, and it's not really. Does it help to burn bills? I have to give that a try. That's just sorry. What do you mean? Yeah, it depends. Yeah, it goes in the right direction because it depends on what is executed first. Yeah, if the assumption is you first remove money from K2 and then you add it to K7, then the bank wins. But no one forces you to do that in that order. If the transfer is from account 7 to account 2, you could still do it in that order, and then maybe what the application code is doing, it's adding first $100 to K2, but then what's omitted here is removing the $100 from K7. Do you see that? It really depends on how the application code is organized. So in that situation, very weird, the customer wins and the bank does not win. So it may also happen. Yeah? So that's not what you want to have. It depends on what you want to have, but the assumption would be that the money is removed and sent to the other account. Yeah? And if this atomacy example is violated, it's obviously violated here because only this operation was not executed, then you're violating this atomicity principle, and then that's not a good transaction. Yeah? That is atomicity, all or nothing is being executed. So this implies you have no half-hearted transactions. The database system, the database, the data must be protected against only parts of changes of a transaction being executed on the database. That's very important. And we will later on talk about this topic. Maybe we revisit this box once we are there. But this basically, atomicity describes what's happening inside a transaction. Atomacy is a property about a single transaction. It's not about the interaction of multiple transactions. That's another thing we will be looking at in a moment. This is about a single transaction. And if you have a transaction like that, the idea is all of that is executed or none of it. That's very important. Okay, atomicity, that's the first letter. The second letter is consistency. The consistency condition is an invariant to the database. It sets a condition to the database. If you think about that, conditions we had already was keys, key columns. You must not enter the same key to the same column twice if it's a key column. Another consistency condition you may think of is something like that. If you select the sum over the accounts table, no matter whether you do that before the money transfer or after the transfer, it should be the same result being returned, because the money you shouldn't have got lost on the way. It's now you have 100 euros that are now on a different account, so the sum must be the same. That's how you could phrase an invariant or consistency constraint. And the letter C in transaction means that while processing a transaction, the database may be arbitrarily inconsistent from the point of view of the transaction. So from the point of view of transaction, it looks like as if you're violating consistency, and it looks like as if you're doing weird things. So you see that, for example, here. At that point in time, after the new account balance was written, assuming that I'm deducting 100 euros from K2, once I write that, I would be violating that consistency constraint. The sum would be different, would be minus 100. If now concurrently I computed the sum over the accounts table, it would be 100 euros less. And that is okay for the letter C, because I'm still within the transaction. From the point of view of this transaction, that's okay. I can mess up with the database state as much as I wish. However, once I commit the C1, I have to fulfill all the consistency constraints again, and which is actually true from my point of view, because if the write 1 to K7 adds the 100 euro, or if the write 1 of K7 does something that such that the consistency constraints are not violated, everything is fine. So if I remove the same amount of money there that I'm adding there, the consistency constraint is not violated. And that is what this letter C is about. So you can mess with the database state as much as you wish. However, if you commit a transaction, if you want to finish the transaction, end the transaction successfully, you have to make sure that you fulfill all these consistency constraints. Here's a list of other consistency conditions. Primary key, as just mentioned. Foreign keys, that's you mark in the schema that this attribute value references the primary key in person, so you can only use IDs here that actually exist there. We talked about that at length in different lectures. Or you could have more complex rules. For instance, you could do something like a professor holds at maximum 3 lectures per semester, and if now all of a sudden you try to add a 4th lecture to that, then the database system could say, no, my consistency constraint says it's at most 3 lectures. I'm rejecting your transaction. You're not allowed to commit the transaction. And it's a long story what you can do with database systems there. So this implies that you need to check the consistency conditions for each transaction. So the database must be protected against changes of the transaction being applied to the database that violate any consistency condition. You don't want to have anything. What is the idea of that? So it was 10 years ago or so, I saw one of the relations from our fantastic lecture planning system. That was back then in, I don't know, it was 2015 or something like that. And there were interesting entries for the lectures I gave. For instance, there was a lecture, Database Systems, Professor Dittrich, given in 2034. That was 2015. So that was obviously violating a consistency condition that maybe what you put there shouldn't be too far ahead in the future, or should be just history anyway. So there were a couple of bad data entries. And all of these bad data entries could be phrased with consistency conditions. Yeah? If you avoid in the first place that users enter stuff that doesn't make sense, you don't have dirty data, you don't have corrupt data in your database system. Yeah? So it makes a lot of sense to phrase it as consistency conditions, and that can be checked before the transaction commits. Yeah? So it's a very powerful mechanism to keep your database consistent. Letter number 3, and that's the really tricky thing, isolation. So concurrent transactions do not affect each other. For each transaction, Ti, it appears like Ti is the only transaction that's executed. What other transactions Tj not equal I do, or their effects on the database, are not visible to Ti. Getting back to our Mensa example, the student canteen, what that means is, how you could fix the situation is, okay, it's really stupid to just allow one student at a time in the student canteen, but what if you gave them these virtual reality glasses? Yeah, you give each student a virtual reality glass, and through the virtual reality glass, the student enters Mensa, and to the student, it appears as if the Mensa was empty. The student doesn't see anyone in the Mensa. Oh, it's totally empty, fantastic, I can do whatever I want, right? There's no one there, it's absolutely beautiful, great, yeah? And you do that for every student and allow for multiple students entering Mensa with these virtual reality glasses. So from the point of view of each student, it looks like as if they own the Mensa, they're alone in the Mensa. And maybe you also have to have noise cancelling headphones because they don't want to hear. Yeah, you see where that is going. Yeah? So you simulate, you pretend that the transaction owns the database system. However, in the background, you have to make sure that things don't screw up and things don't go wrong. Yeah? But it looks like, at least from the transaction, from an individual transaction, that it owns the database system. And that is an important idea behind isolation. Yeah? So a sufficient condition we will be recurring to multiple times is that the execution of two transactions, if you can prove that this is equivalent to one sequential execution of both transactions, then you're done. Yeah. So again, I think the student example is actually pretty good. Can I use it everywhere? So you have two students, Alice and Bob. Alice enters Mensa, does something to Mensa, maybe whatever. Yeah, those are the situations. So first Alice. Yeah, and then Bob. They enter Mensa, if that's our timeline. That's one option. And the other option, let's say it's option 1. Option 2 is, this is pipe notation, first Bob, and then Alice enters Mensa. And they do something to Mensa. Yeah, they remove food, or maybe they spill food on the floor, maybe they destroy a chair and a table and stuff like that. And what we will be looking at is not the single pipe symbol, but this double pipe symbol. Saying, yeah, they somehow entered Mensa, they were at the same time at Mensa, and they somehow interacted and no idea what they did there. But after that happens, Mensa is in a specific state. Yeah? If Mensa is a capital, our relation, so to say, Mensa, Bob concurrent to Alice, then after that, our Mensa is in a specific state. And we want to answer the question whether the state is acceptable, the state of the Mensa. And it is enough to show that, okay, now the state of Mensa is equal to Bob was in the Mensa alone, and then Alice was in the Mensa alone, and that changed somehow Mensa in a specific way, or the other way around. Yeah, the other option, that's option 2. Alice entered Mensa, did something to Mensa, and then Bob entered Mensa in a serial fashion. And that changed the state of the Mensa in a certain way. And if you can show that this state is equivalent to that, or, not an and, very important, an or this state is equivalent to that, then you're good, everything is fine, because then you can show that, oh yeah, Mensa actually now looks like as if I had executed it in a serial way, like this or like that. Serial is fine. Yeah, that's perfect. Nothing can go wrong. There's, by definition, no concurrent actions being taken. And the only thing you need to prove is that here, that could also involve multiple students / transactions, of course. But if you can show that the ways the students messed up Mensa is equivalent to a serial messing up of the Mensa, everything is fine. Yeah, that's the quality of that slide. Yeah, is it clear somehow? Yeah.
The way you said it, it implies that like the order in which they both enter the Mensa does matter. Like
For concurrent?
for the sequential.
Yeah, but, oh yeah, sure. But that's the definition. If you go back to the definition of how we define serial, where's that? Here, T1 first, and then T2. So T1, student 1 enters first, and then T2 enters the Mensa. So once T1 is done, only then T2 is allowed to enter. So that's a serial execution. First Bob enters the Mensa. Once Bob is done and leaves Mensa, Alice enters Mensa. That's one pipe symbol.
But if let's say Bob enters Mensa and then Alice enters the Mensa is equivalent to Bob and Alice both enter in Mensa.
The state after that happened, yeah.
Why would the state of Alice first entering the Mensa and then Bob be different?
It doesn't have to be different, but it can be different. Yeah, I'm just saying from the point of view of a consistency argument, it's enough to show that whatever happened here, when both entered, I don't know who entered first in this scenario, I don't know how they interacted, I don't know what happened, I don't know how long they stayed. I'm just saying they entered at some point, both left at some point. Now the Mensa is in the new state, and if I can show that that state is equivalent to either this or that, I'm fine, because then the argument is reduced to they could have done it like that in the first place, right? Yeah, if they had eaten in Mensa like that or like that, yeah, that's obviously a serial execution. Everything is fine. Yeah? That's the heart of the argument.
Why can't that be an and?
It would be much stronger if you prove like, okay, if you have to prove that it is equivalent to this or that, but if there's a conflict somehow on the stuff they changed, yeah, that could end up into that actually, we look at some schedules later on. I'll answer that later. You will see where that goes. Yeah? Okay. What was I? Isolation. Yeah, so isolation, how did I get there? Oh, so here we were on that slide, right. Okay, yeah, so that's the core of the argument we will be using later on when you will have these exercises where you basically have you have schedules of transactions with the individual operations, and then you need to show, oh, is that fine or is that not fine? Is it equivalent to something serial, one of those, or not? If it's equivalent, everything is fine. Yeah? If not, oh, we have a problem. So that's letter 2, no, letter 3 already. Yeah, this is again saying, okay, if it's like that, so we can't just allow everybody to do stuff with the database. There has to be some algorithm, so some control over that, and that's what we will be looking at. So the algorithms will be controlling the I and the C part, and that's what we will be seeing later on. Okay, the final letter is durability, saying if a transaction T commits, the effects of its write operations must be preserved in the database no matter what. Yeah, so no matter what. So the transaction commits, yeah, and assumes that the change operations, the money transfer in that example, are persisted in the database system, and then whatever happens, the database must not forget that change. The database system must make sure that those changes are never lost. Yeah? And the So that could be examples like power failure. Even in the case of a power failure, if the database system said, no, I committed the transaction, the database system must still protect against power failures. And actually, database systems can do that automatically. Yeah? But then you run into questions like, okay, were the changes persisted on hard disk, SSD, before the power failure, which ones? What if the data center burns down? Yeah, where you had your backup, maybe you replicated it to another data center, things like that. Yeah. So it basically quickly leads to an argument like if you watched Star Wars and there was this Death Star destroying one of the planets, if all of the data centers of the planets are destroyed, the data is gone. There is no durability at that point anymore. Yeah? Also, another famous example was a couple of years back, a developer reporting on YouTube that the guy had a laptop and 2 external hard drives on his desk with copies. So he had 3 backups. What happened? A guy broke into his apartment and stole the laptop and the 2 backups. Is the data still durable? From the point of view of the thief, kind of, but from the point of view of the guy, not so much. Yeah, so durability is depends on your point of view. Yeah, so you have access to the data. Yeah, then you could claim, yeah, it's kind of durable. Another example is you encrypted your data and lost the key. Is that durable? Yes or no? Maybe someone else. Yeah, you encrypted some super important data, maybe the database or whatnot, and then you lost the key and you can't break the encryption. Yeah? The data is preserved, kind of. Yeah, that's true. You may wait for a couple of quantum computers to break it and allowing you to enter it. But is it durable? It depends on how you want to define durability actually at that point in time. Yeah? That's where your argument is going. It's preserved. It's still there. You just have no chance to look at it, right? That's kind of, you lost the key. Yeah, maybe it's durable, but it doesn't help you. You can't do anything with the data. So it's a very, there's not 100% durability. You can always increase it, make it 99%, 99.9, 999, tra-la-la-la-la-la, and build these scenarios, but there's no perfect durability. However, the idea is that the database system or the installation of the database system makes sure that the durability is super high. Yeah? And so you have to look at replicas, backups, and stuff like that. Okay. Yeah, it's also something for the database systems lecture, not so much this big data engineering lecture. So with that, we can now enter serializability theory and define a couple of terms that are important there. The first is the schedule, also called a history. History is a bit misleading because it looks like as if it already happened, but we are also using this as an argument to what's about to happen or what could happen. A schedule, a plan of how you interact the operations of different transactions. So a schedule specifies for a set of transactions T1 to Tm, the order of the read, write, and commit or abort operations. So the order of the individual operations, how they happen in which order. We write down a schedule as a strict partial order over the individual operations. And that's important. Note that the order among the operations inside the transaction is preserved. So at no time, if a transaction defines a specific order, at no time we are allowed to change the order inside a transaction. That's forbidden. But what we can do is, if you have 2 transactions, one finger is an operation in transaction this hand, and here's another transaction, and there's 4 operations. Yeah, so I can't change the order here of the fingers, but you can change how they interact, how they are intertwined in those schedules. That's okay, but within a transaction, no way we change that. The order must be preserved. Okay, and for notation, I will leave away the B for the moment because I will assume, there's a read or write with an index of a transaction that defines the begin of the transaction. Makes my life a bit easier. So I will show a couple of examples for schedules in a moment. But before that, we have to define a conflict operation. So what's a conflict operation? That's an argument you do for two operations. Yeah? So a select or an update, insert, delete operation. We are just using the abbreviations, as I said before. So we have two read or write operations, OI, on a data object A and PJ on a data object B. And this O can be an R, or it can be a W. So O can be read or write, and the same holds for P. And now I want to define whether these two operations have a conflict. And that's then called a conflict operation. And those operations are in conflict if these three conditions hold. So they must belong to different transactions, the operations. They must access the same data object, and at least one of them is writing. Again, if two are reading the same data object, who cares? Because it doesn't matter. But if one of them is writing, then things can go wrong. And here are a couple of examples. So you have a read operation of transaction 1, a read operation of transaction 2. Can't be a conflict because nobody is writing. So it's this strikes different transactions. It's the same data object, but this not so much. One of them is the write operation is not true. So this is no conflict operation, only read operations. Yeah, when you go through the other examples, a similar argument, you always check the three conditions here. So transaction 1 already fails within the same transaction, who cares? Transaction 1, transaction 2, that's fine. Same data object, that's fine. Oh, one is writing, yeah, that must be a conflict operation. All conditions are met. Same for the other examples. Transaction 1, transaction 2, fine. Same data object, yeah, it's A. One is writing, yeah, both are writing actually, so that's a conflict operation, definitely. And the final example, transaction 1, transaction 2, same data object, well, not so much. A and B already wrong, so that's not a conflict operation, different data objects. So these conflict operations will become important in a moment. But now for our schedules, there are two ways to specify them. One is with total order and the other is with partial order. So total order is something like that. It's really a linear chain of these individual operations. We saw that already here. That was this one transaction doing the money transfer. And now if you have another transaction doing another money transfer like this, yeah, transaction from Bob transferring 100 euros from account 7 to account 2, you could define a schedule with a total order for these two transactions. And then you see, also marked it here with colors. The red is in between the blue, and here's red again, and so forth and so forth. So that is a possible schedule with total order. And from a theoretical point of view, we will have to reason whether that is okay. Yeah, so we also have to come up with algorithms to decide whether that is okay at runtime. That's another story, but for the moment, on the conceptual level, we have to discuss whether we have such a schedule. Is it okay? Would it be okay to execute this stuff? So how can we decide whether that schedule is a good idea? That's what it boils down. Yeah, that's a serial. So this is a schedule with a total order, strictly serial, linear, chained operations. But you could also define it as a partial order, which is much more useful, and for that you need the conflict operations. Here the idea is you do not force all the operations into a total order, but specify at least the order for each pair of conflict operations in the schedule. So for instance here, if you have these two transactions, blue and red, here, well, that's definitely in conflict, same data object, different transactions. One of them writes, both of them write, yeah. So you make an arrow and specify, which is executed first. So in this example, this write is executed before that write. Yeah. And then you can also simplify that. For instance, you could say, I leave away this one, for instance, because that's transitively clear how the order is. Yeah. If you look at, let's remove my markings. Yeah. That's basically this one and that one. following this definition here, at least the order for each pair of conflict operations where there should be an arrow like that, but you could say, well, that is before, this has to be executed before that, yeah, and that has to be executed before that, so it's implicitly defined already anyway. Yeah? So you can simplify the graph a little bit to not make it too cluttered. Yeah, right. Yeah, and with that we can define a conflict order. The conflict order of a schedule is a subset of S that orders only the operations of the conflict operations. Yeah? So the pairs of conflict operations. So if you have conflict operations in your schedule, what you specify is, okay, I have this pair of conflict operations. I now define in which order do I execute these conflict operations. So you don't say you order all of the individual operations anymore, but just the conflict operations. Because it turns out that that is the interesting thing you need to, again, an analogy that pops into my mind is whenever you sit in a car on your bicycle and you enter a crossing, you can actually think about what is a conflict operation on the car crossing. Yeah? So here's whatever. That's the crossing. Oops. Yeah, and there's a car operation, a car approaching here, going that direction. There's a car going in that direction on the straight ahead lane. Yeah, and there's another car maybe going in that direction or something like that. It's the same argument I'm making here. Now you can think about, are these two cars in conflict or not? Yeah? So another example here would be, for instance, yeah, you're here with your bicycle, approaching with your bicycle, yeah, and there's another car that's turning to the right. Are you in conflict with that car? No, because once the car left the crossing, you're not there yet. You don't have a chance to be in conflict with that car. If you were here, well, that's another story. Then you're in conflict. So if those cars are equivalent to the operations in our transactions, now we're looking at pairs of cars that may crash into each other. That's what I'm trying to define here. I try to define, okay, we have the crossing, we have cars that may potentially crash into each other. To avoid those crashes, and not even avoiding the crashes, here I'm just defining a specific order, not saying whether that will lead to a crash. I'm just saying, okay, this car drives first, then that car, and then that car, for instance. Yeah? But you can always reason about which cars are in conflict anyway, because I can make the argument here, that car and that car are not in conflict because they're in opposite lanes riding straight ahead, so they're kind of not operating on the same data object. Yeah? They're not riding over riding over the crossing. However, this is obviously in conflict with that one, and that is obviously in conflict with that one. So my conflict operations are this and this, but those two are not in conflict. Yeah? Same argument here. Yeah? So what can go wrong? You're focusing on the stuff where you really screw up the database state and we ignore everything else where you know nothing can happen, everything is fine. Yeah? That's the gist of this argument. So, and that's basically the argument already alluded to a moment before. So we will have two kinds of schedules. One is a serial schedule, and that says a schedule S is called serial if all transactions in S are executed completely one after another. That's a single pipe symbol, now the schedule variant of that. So for example, if you write like T1, T1, T2, yeah, in this notation, I don't show the individual operations. But if I show the individual operations in a schedule, yeah, that's what I see. Yeah? You see this is transaction 1 and this is transaction 2. That is a serial schedule. The same holds for the second. The second just says that's T2 before T1. Oops, this is supposed to be a 2. Yeah? That's this schedule here. Yeah? That's just a detailed way of writing that schedule. And the third example, however, is not serial. because here you see the stuff is somehow intertwined. Yeah? So that's just notation. It's really super, it's the same notation as we had for this, the state transitions of a database. Now we have it for the individual operations in the schedule. So, and that brings us to the term conflict equivalent. And that's basically what I already alluded to, how these things work and how do you show that the schedule is good. So two schedules, S1 and S2, are called conflict equivalent if all operations of conflict operations in S1 and S2 are specified in the same order. If all operations of conflict operations, so I'm not saying that all operations are specified in the same order and would have exactly the same schedule. I'm just saying, yeah, there's a subset of conflict operations between these two transactions. And if they are executed in the same order, I say they are conflict equivalent. So they're conflict, yeah, so the conflicting cars, yeah, pass the crossing, drive over the crossing in the same order. But everyone who's not in conflict on the crossing, I don't care about. You drive in any order, I don't care. But the conflict stuff, that has to be specified. Yeah? That's what the argument is saying. So here's a couple of examples again. So S1 and S2 are conflict equivalent. So the only change you're seeing here is this write operation. And here, from there, I'm swapping it down to that operation. So I'm swapping these two operations in the schedules. And why is that okay? Yeah, because that's not, these two are not a conflict pair, not a conflict operation. They operate on different data objects, so they're not in conflict. I can swap them in the schedule without changing the order of conflict operations. That's absolutely fine. I can do that. Huh? In contrast, if you look at this here, yeah, assume you did something like that. So that's the same as schedule 1, just that these two operations were swapped and everything else is the same. But that's not okay because those two are conflict operations. Two different transactions, same data object, and one of them is a write operation. Those are conflict operations, and I swapped the order. So I changed the order of the two conflict operations, and that's not okay. So that would not be conflict equivalent for the, with regards to this S1 schedule. Again, that's what I said before, the relative order of operations within a transaction must never be changed. That's forbidden. Yeah, and with that, we can define conflict serializable. A schedule S is called conflict serializable if it is conflict equivalent to a serial schedule. A schedule S is called conflict serializable if it is conflict equivalent to a serial schedule. And that brings us, let's again, actually, I explained that example already. So Bob does a couple of things in Mensa. Yeah? Whatever. So if Bob is my transaction 1, that's T1, and that's T2. Same situation, Bob does a couple of things, enters Mensa, grabs a plate, sits down somewhere, stuff like that. These are individual operations. I'm not showing here, I'm just saying Bob, right? Yes, there's a schedule here induced by that transaction, and there's a schedule here induced by whatever Alice is doing. And I said before in the example, okay, those are somehow intertwined. Yeah? Somehow scheduled first this and that, whatever way, however that happens, I don't care. And this argument is saying, okay, if you now can show that this schedule here, however that looks like intertwined, can be, is equivalent, or is conflict equivalent, that's the important term, not equivalent, conflict equivalent. In other words, the conflicts, the order in which the conflicts were executed here is the same in any of the serial schedules, then you're fine. Yeah? So you're proving that, okay, the conflict operations that happened here were executed in a specific order, yeah, for all the conflict operations here. And if you can show that the order that was used here is the same conflict, it's the same order for those conflict operations in any of the serial schedules, then everything is fine. Then you proved that, that the conflicts were in the same order as in the serial schedule, and that makes sure that this is conflict serializable. And that's the argument you will see a lot on the assignments as well. So if you look at an example, what that boils down to is you can swap non-conflict operations. Where's my... Yeah, so you have a schedule like that, and now what you're allowed to do, you can bubble the operations to the left and to the right with the goal to end up with a serial schedule. That's the idea. Yeah, so you can, for instance, this R2B and W1A can be swapped. It's different data objects, so I swap it to something like that. Now we have these two blue operations here, and all the red operations are there. The commit now can be swapped, can be bubbled through the entire schedule. That's another rule. So basically you end up with something like that. So through bubbling operations, so swapping the non-conflict operations, you ended up with what we called a serial schedule. That's T1 before T2. I just defined that 2 slides ago. And that is a proof that this schedule, as shown on top, with some intertwining, is conflict equivalent to this serial schedule. And as you showed that, this is conflict serializable. And that's the most important argument when reasoning about these schedules. Yeah, something to digest. I'll give you a bit more to digest for next time. Yeah, we can have 5 minutes to look at the conflict graph, also called the precedence graph. It's also something that occurs all over the place in computer science. That's a higher level aggregate view on your schedule, if you wish. Yeah, so the conflict graph of a schedule S consists of a set of transactions. Those are the vertices or nodes, and an edge for each pair of transactions from S that have a pair of conflict operations. So for instance, if you have your schedule here on the left and the arrows denote the conflicts between operations of these two schedules, then you provide an aggregated view on the right. And you're saying, okay, there's a conflict between T1 and T2. Yeah? Here on the right, I'm not saying which operation triggered the conflict. I'm just saying there's something that can go wrong. There's a conflict operation between transactions T1 and T2. Yeah? And this conflict graph or precedence graph is also called a waits for graph in the systems community. Can be used also algorithmically to detect these kind of situations, because obviously if you build a graph like that and you find these kind of things, you can use that to schedule entire transactions. Yeah? You see, oh, there's an edge between these two transactions, so I better don't execute them at the same time because things can go wrong. Yeah? So you first execute T2, for instance, and once T2 is done, you execute T1. Yeah? So there are a couple of algorithms in that space that do that stuff. There's an aggregated view on what we call a schedule in this lecture. So here's an example for a schedule, and then the graph, the conflict graph, precedence graph, waits for graph. I think there are even more names for that, however you want to call that. So we have 3 transactions. That means there are 3 vertices in the precedence graph, T1, 2, and 3. And now I change the schedule. This is not about bubbling. This is about changing the schedule slightly. So S2 is almost the same as S1, except I add another operation here. I add this read operation. And for that, I have to add another edge here. So I have to add a new edge. Why is that there? Because in the schedule S2, there are the conflict operations W2B and read1B. Yeah, so this is in conflict with this one, obviously. Those 2 are conflict operations. And therefore, now I have to add an edge here. Yeah? Because here it's specified 2, transaction 2 is before 1. Yeah? And that adds an edge to that. And that also, and now you see in the graph you have a cycle. And what I just said, yeah, now it's not as easy. You can't just execute T1 before T2 or T2 before T1 because they're intertwined. So if you have a cycle like that, this is a cyclic graph and not a directed acyclic graph anymore. So you see it here, that's a directed acyclic graph. There's no way you can, when you start at any node, there's no way you can move through the graph and end up at the same node. Yeah. However, in this situation, you can start at T1 and then go round and round and round and round. The same holds for when you start for T2. That's called a cycle. Yeah. And conflict serializability maps to this conflict graph as follows. A schedule is conflict serializable if and only if the associated conflict graph is cyclic free. Yeah, so that's another way of seeing the problem. If you build this conflict graph and you find out there's a cycle, then you know that doesn't work. Yeah, and then a very natural algorithm is to say, okay, maybe I can remove nodes from my conflict graph, aka I remove some transactions from the conflict graph as long until I end up with a DAG, with a non-cyclic graph. And then you know it's conflict serializable actually. Yeah. How much time? 2 minutes. Okay. Yeah, we will catch up on that next time again and continue that. So for next time, it's really important you understand the basic concepts. There's a ton of material on my YouTube channel. There's again another very gentle explanation on transactions and asset in German and in English. Make sure you understand these 4 letters. It's super important for everything that follows. It's the absolute foundation for everything that follows. You can also read it up in the books as usual. And make sure you understand the basic terminology of schedule, conflict operations, read and write operations, of course, and conflict serializability, because we will build up on that next week, Thursday. Yeah? See you next week, Thursday. Thanks.